Wasn't she made a movie?
Yeah, she is. But she hadn't told me specifically about missing class. But it's still a distinct possibility. Oh, okay. I'm getting a message. Come on. Okay, yeah, she will not be joining us. Okay. And letting you know that I actually remember to start recording. Okay. All right. Okay, so now that everybody's here is going to be here, all more questions?
Last time my Wi-Fi, well, not even the school's Wi-Fi wasn't great at first, and I didn't hear Walker ask her question, but I think I was along the same lines where I'm not sure, like, what the form the answer's even in on 7.5.2, the first one.
Okay. Well, actually, the final answer can be given in words. So actually, that's probably best. I'm trying not. I'd be careful not to give too much away, but because after, well, and I'll, well, yeah, I've already gotten a message that this problem is posing some difficulty, generally speaking. So, okay. As far as how to proceed, hold on. Okay. For this problem, the best thing to do is that if you work with, because this is a problem statement deals with a general value of n, that you have 1 point x naught that's repeated n plus 1 times. And then what's a polynomial of degree n that satisfies all of those conditions? So what I would suggest is you try working this out for just the very first specific values of n equals 0, 1, 2. And what I'm hoping is that when you do that, you will see a pattern in these for polynomials that you're actually getting. And now, as far as how you would just give you the answer, I guess there's a couple ways you could do it, because one is you could simply describe a pattern in general from what you see from each specific n, so that would be fine. Or the polynomials that you get, they actually do have a name that describes them, and you can just give a name. And no one had better say it in class, or I'm flunking you. Okay, so.
So you said evaluate at the different n values. Do you do that for each derivative?
Yeah. So for example, yeah. So when n equals 0, then you have a polynomial degree 0 constant that must equal f at x naught. And then when you go up to degree 1, you'll have 2 conditions to satisfy. So at x naught, it must equal f of x naught, and its derivative must equal f prime at x naught, and so on. So in every case, you're going to have a system of n plus 1 linear equations for the n plus 1 unknowns, the coefficients. So for these small values of n, then it's feasible to actually go ahead and solve a system and get the coefficients. I guess past n equals 2 is a real pain, but I think that'll be enough to see what's going on.
Thank you.
Alrighty. Okay. So good luck with that. Others? Okay. So I will continue with splines. Okay. My document up here. Okay. So last time we were dealing with linear spline, so a piecewise linear function that matches a function f at given points. So basically, it's taking those points in the graph of f and connecting the dots. But a piecewise linear function, while it's relatively simple to come up with, has a drawback that it's not smooth. It's continuous, but it doesn't even have a continuous derivative. So if you want a smooth function that fits given data, piecewise linear is not going to get the job done. But a cubic spline is much better for that purpose. Okay, now I'll make sure I have my notation consistent with the book. Okay, so a cubic spline is a function s of x of this form. So what I'm going to give is the definition of a spline or a formula for it on each piece. Okay, so we have s of x is equal to, so on each piece, I'll have si of x, so sort of piece number I. And it has this form, a coefficient, ai, for constant term, and then bi x minus x, I minus 1, plus, so we have a polynomial in x minus xi minus 1, which I'll explain in a moment why that choice is made. Cubes. So that's the formula that applies for x in this subinterval. All right. So as before, same notation as last time, and I'll just restate it here. That we have these points that cover the interval AB. So x naught is A and xn is B. So we have, because we have n plus 1 points in total, we have n subintervals between them. So on those n subintervals, this is how the spline is defined. So so the way that each piece of a spline is defined, the way it's written is called shifted power form. Now we've seen power form where you just have like coefficient times x plus coefficient times x squared and so forth. But here it's instead of powers of x, it's powers of x minus something. And I'm using the left endpoint of each subinterval. Oops, that's left. And we could use any form for this technically, but using shifted power form is convenient for describing the criteria that the spline is supposed to satisfy. Okay. So my next point I want to make is each piece, being a cubic, naturally has 4 coefficients. We have n pieces all told. So we have 4n coefficients to specify that will define the spline completely on all of AB. So since we have 4n coefficients, we need 4n equations to specify them uniquely. So, what I'm going to do is impose conditions on these coefficients so that we can get a system of equations to solve for them. Okay. All right. So here's a criteria that the spline must satisfy. Okay, first, it has to fit the data. So what that means is SI of xi minus 1 is equal to the corresponding y value. So if I plug in the left endpoint for each piece, then I need to get it must equal the y value at that same point. Okay. And this is true for I equals 1 to up to n. Okay. Now, if I were to substitute this x value into this formula here, so this value turns out has a very simple expression. So can anyone tell me what this ends up being equal to?
Just AI.
Oh, very good. All right. So yeah, because all of these will go away. That's an advantage of a shifted power form. We can see right away. All right. So now the A's are already determined. So that means we have because remember I said we had to specify 4n constraints, 4n equations for these coefficients. Well, here's n of them right here. So we need 3n more equations to pin down the B's, the C's, the D's. All right, so then I need to move to next criterion that it has to be continuous. Now here, I've substituted the left endpoint into each piece. Well, now I need to see what happens when I plug in the right endpoint. So if I plug in xi into this piece, then it must be equal to the value of the next piece at the same point. They have to match up. But we already know what that is. That must be equal to yi, which is also equal to ai plus 1. So because we have two neighboring pieces, that means this condition can only be applied at the interior points. So starting from x1, x2, and up to xn minus 1, because we have pieces on either side. So this is true for I equal 1 to up to n minus 1. Okay. Now, okay. So now, but actually we go a step further because notice I've dealt with for y values starting from 1 up to, or sorry, from y0 up to yn minus 1. Here I've dealt with y1 up to n minus 1. Yn has not been accounted for in any of this, but I'm going to deal with it now. So I can impose a condition Si of xi equal to yi for I equal n, because everything for I equal n, all of these things are defined. So we can fit the last y value. So at least that piece of the given data is accounted for. All right. Now, so far I have n equations here. I have n minus 1 equations here, and then one more here. So I have a grand total of 2n equations, but I need 4n, so I need 2n more. So this one here is not really a continuity condition, because that's about agreement between two neighboring pieces, but it's a convenient way to express it like these continuity conditions. Are there any questions up to this point? All right. Now, more criteria. I'm not really sure why I keep yelling at criteria, but whatever. So we have a similar condition to this for the first derivative. Okay. Sorry. I should not move on to that just yet. Need to go back to this condition. I have more to say about this. I need to tell you what this means in terms of a coefficient to A's, B's, C's, and D's. So if I take xi and substitute it in here, then I'm going to have xi minus 1 raised to powers. So here's how I'll write it out. So we have an equation that has ai plus 1 on the right side. And on the left side, I'm going to have ai plus bi. Now, based on the formula, I'd have this. X I minus x I minus 1. All right, so I'd have this. Now, and this can apply for I equal 1 up to, whoops, I going from 1 to n, if I need to make a definition here. an plus 1 equal to yn for convenience only. Because I only have n pieces. I don't really have a coefficient an plus 1. But if I define it to be yn, then I can write the condition this way. So again, it's just notational convenience. And while on the subject of notational convenience, here's another. Here I have the spacing between two consecutive points. So I'll define a variable for that. I'll call it hi is xi minus xi minus 1. Then I can restate this more concisely. So anywhere where we see xi minus xi minus 1, that could just be hi. All right, so this is the condition that we're going with to ensure continuity and also fitting the data at the last point. So some applications, the points may be equally spaced. So we just have one variable h that covers the spacing between them. So that becomes extra convenient. All right. All right, questions up to this point before I talk about derivatives. All right. So first derivative, in terms of s, or pieces of s, we must have si prime at the as right endpoint must be equal to the next piece. Where'd it go? Oh, sorry, next page. At the same point. And these are at the n-1 interior points. Now, in terms of coefficients, we could get an equation much like this one, but it has to apply to the derivative. So, and actually, you can think of it in terms of taking a derivative of this. So the ai will go away because that's a constant. And what we would get is bi plus 2ci plus 3dihi squared. And you can see where that comes from by taking a derivative of this. It just works out that way. Really, to be rigorous, you should go up to here, take the derivative of this, and plug in xi. But that's what you would get as a result. And then, if you also take a derivative of a next piece, so piece I plus 1, what you would get is bi plus 1. Okay. So that ensures that the first derivatives meet up in a continuous manner at these interior points. All right. So far we have n plus n minus 1, 3n minus 1 conditions. I still need n plus 1 more to complete the set. Well, we have a second derivative. Has to be continuous. So si double prime at xi must equal the next piece at the same point. I want to express that in terms of a coefficients. And based on how I got this one, what do you think that equation should be? There'll be something resembling this, but we're going one derivative deeper.
We're only at C and D's now.
Right.
But you want the exact. So 2CI plus 6DIHI. Oh, sorry. Equals CI plus 1.
Almost.
Oh.
Well, if you were to go here, take the second derivative. Oh wait. Yeah, the original.
I couldn't hear you quite.
Sorry. Second derivative of this. When we're looking at piece number I plus 1. You were close.
I guess just CI, or what did I?
Like if you're taking the second derivative of this.
Right.
Okay, well these terms would go away because they're linear.
Right.
What happened to this one?
You pulled the 2 out front, and it's only to the first power.
Right, and then for first derivative, and you do it again.
Right. Oh yeah, and then then it's just 2CI.
Well, yeah, that's what you have over here on the right.
Right.
What do you have on the right side? So it's like this, but with C. So here on the right side.
I guess just CI, or 2CI. Sorry.
Okay.
I think I'm missing something. Yeah.
Remember the very first answer you gave for right side.
CI plus 1.
Yes. You were so close with that. And then
CI plus 2.
Okay.
I don't know. I'm missing the point of the right side of the equation, I think.
So you correctly got that this index applies the first time. Then, so CI plus 1 is involved. So then I had you examine the second derivative from up here.
Mm-hmm.
And what was the new thing you got from doing that?
Oh, do I need to put a 2 out in front of the I plus 1? Like 2 I plus 1 in parentheses. So C of 2 like subscript 2 times I plus 1.
Look what happened here. Going from here, look at the left side. See what happened going from here to here? It's almost like if you're taking a derivative with respect to h in a way, where here there's no h, so that term went away completely.
Mm-hmm.
H to the first power, you take a derivative and you get.
Oh.
So you did all this correctly. Now for the other piece, you just had to go back up here to see. Okay, here's a factor of 2, and you see, like I said, you pull the factor of 2 down.
Uh-huh.
So that would not go into the subscript. All right, so the first two answers you gave me were both close in different ways. So it's almost like if you needed to merge them and you'd have the right thing.
Were the first two answers I said CI plus 1 and CI?
The first answer you gave was CI plus 1. The second answer you gave was 2 CI. So both of those answers were very close, but each was missing in a different respect.
Okay. So 2 CI plus 1.
Bingo.
Okay, sorry, that took a while.
Okay. Yeah, because once I saw you going to mess with a subscript, it's like, okay, I gotta really get back in.
Yeah, I think I was just, as far as following for now, just kind of going off the patterns of before. Yeah. But I didn't realize I need to pick up the coefficient out front as well.
Yeah. Well, it's harder. It's easier to see it from the left side and the right side, because here you don't have a whole derivative worked out. So that's why I brought you up here, where the 2 would come from.
Gotcha.
So, because you had everything right the first time, except for the factor of 2.
Okay.
Yeah. Okay.
There.
All right. Now, okay. So now we have all these criteria imposed on. So the spline itself, first derivative, second derivative must be continuous, has to fit the data. Now, if we do condition counting, like all these conditions that have been imposed, what do we have? We have okay, n here. We have total of n here. So that's 2n so far. And then from a derivatives, we only get n minus 1 here and n minus 1 here. So we have a total of 4n minus 2 equations to specify 4n unknowns. Well, that's not enough. This does not give a unique solution. So we have to specify 2 more conditions on these coefficients, and that will specify the spline completely. And the thing is, there are different ways of doing that. I'm just going to talk about a couple of them here. So what we impose are called boundary conditions, because we have 2 boundary points and we need 2 conditions. So it makes sense that whatever we're going to specify, it should relate to the boundary. So here's some examples of boundary conditions. The first is natural boundary conditions. And that just stipulates that the spline as a whole, its second derivative at x naught and at the right endpoint, xn, must be 0. Now, what that means in terms of coefficients is so C1 must be equal to 0. And so the reason for that is, oh wait, let me check something here. I might have. Okay. Yes, C1 is equal to 0. Because if I look at the second derivative from up here, for the first piece, well, the second derivative would be 2c1 plus another term. And if I plug in x equal x naught, so I equals 1, then this term would become 0. The only thing I have left is C1. So really, the second derivative at x naught is equal to 2c1. Therefore, c1 has to be 0. All right. So that's one condition at the left endpoint. Now, what about the right endpoint? Well, that would come from here, like an expression of this form for the last piece. So all right, I'll fill in the 2 here just so we can see that's what the second derivative at the left endpoint actually is. For the right endpoint of piece n, it's equal to this. So 2cn plus 6dnhn must also be equal to 0. And this comes from a general formula for the second derivative. So that'd be 2ci x minus x I minus 1. Whoops, that's wrong. Plus 6di. Okay, that's the second derivative. So for piece number 1, I equals 1. If I plug in x equal x naught, this goes away and left at 2c1. On the other hand, if I have the right endpoint, so I want to see what's happening at xn, I let I equal n, so then I have xn minus xn minus 1, but that's the spacing hn. So that's where these two expressions come from. So questions on these boundary conditions? All right. So that's one kind. The other kind of boundary condition is clamped boundary conditions. So this is in for a special case where there actually is first derivative information about the data available. So we specified the boundary that s prime of x naught is equal to z naught, and s prime at xn is equal to z n. Whoops, that's lowercase n. All right, so if a derivative of a function you're trying to fit is known at these 2 points, then we specify that. So again, we want to express these in terms of the coefficients, a, b, c, d. All right, so I'll state this up front. I should have done this last time. S prime, si prime of x has this formula, bi plus 2ci x minus x I minus 1 plus 3di 1 squared. All right, so what we get is if I plug in, if I take I equal 1 and plug in x minus x equal to x naught, these 2 terms go away. So we get b1 is equal to z naught. Similarly, sorry.
Are the x's the same as xi?
okay, way I've written it here, no, x is a variable. But like for example, for this case right here, to find the value at the right endpoint, xn, I needed to take the last piece, so I became n, and then I set x equal to xn. And that's where the spacing came in.
Okay.
And I need to do that again right here. For the value of a derivative at the rightmost endpoint, I set I equal n. So that's going to give me bn plus 2cn. And then I plug in xn, because that's where the condition is imposed. So I have xn minus xn minus 1, which is hn. And then similarly for the last term. Whoops, that should be dn squared. And that has to be equal to whatever value is prescribed here. Okay. All right. So choosing boundary conditions like these gives you a full set of equations. We have 4n unknowns, 4n equations. I will briefly mention one other kind of boundary condition. What are called not boundary conditions. And that specifies that S triple prime, that's the third derivative, is continuous at the points x1 and xn minus 1. So the interior, the leftmost and rightmost interior points, we have even more continuity. So first derivative, second derivative continuous throughout, and then at these points that are near the boundary, the third derivative is also continuous. Okay. And a lot of, I should mention, these are the default conditions used by MATLAB's Spline function. Because these are a good choice, just because clamped is only good if you have derivative information available, which you might not. And natural boundary conditions, it's questionable how natural they really are. You're basically saying that your function behaves like a linear function near the boundary, and maybe it doesn't. So not or not is a good default. Now, I will. One thing I need to point out though is in the book, I made a terribly erroneous statement that I'm actually kind of embarrassed about. I make a claim in the book that not or not and natural are the same. Like one is that the two are synonymous, and that was due to a gross misinterpretation of MATLAB's documentation that led me to that misconception that I held for years. So no, they are not the same. Now, so in fact, MATLAB's spline function does not do natural boundary conditions. So it does not or not by default, and it gives you a way to specify derivative values if you want clamped. But natural is not on the menu as far as MATLAB is concerned. So I goofed there in the book, and it'll be fixed in the next edition. Dang it. Okay. And so, but none of my colleagues see that, and then I'll end up being the numerical analyst equivalent of disbarred or something. Okay. So, all right. So that's all I'm going to say about this particular boundary condition. Okay. Questions up to this point? All right. Now, all of the homework problems for this section are actually on the piecewise linear stuff, except one. Number 5 deals with cubic spline of natural boundary conditions. So I'm gonna, let's see. I need to unshare and reshare. Okay. So if we look to the book here, I'll make this a little bigger. Okay, so here's number 5. So the task here is to show that if natural boundary conditions are used, then you could actually come up with a system of equations for just the C's, and that will determine a spline completely. So notice I have C2 up to Cn. The reason why is that C1 is already known. It's known to be 0 in the case of natural boundary conditions. So the task in this problem is to show that the equations that have already been given for different criteria, fitting of data and continuity of a first and second derivative and the natural boundary conditions, is equivalent to this system. You know, this matrix times your unknowns is equal to this right-hand side. So what I will do, this problem is a pain. So, and you know, if I say it's a pain, it must be bad. So I'm going to give some preemptive advice for this problem. And that is, start with a right-hand side. So the idea is, if you form these expressions, notice we have a difference of a value, consecutive a values, minus a scale difference of other consecutive a values. Then you can show that this is equal to what you get on the left side of the system, this matrix times this vector. And how this would go, because the algebra is going to be a pain. Be super careful. Here are the same equations that I typed out earlier for continuity, first derivative, second derivative. Notice here, I have AI and AI plus 1. So if I take AI, move it to the other side, now I have a difference of A's, like in the right-hand side vector B, expressed in terms of the B, C's, and D's. So then I can write out this equation for I, and again for I minus 1. And then I can have a difference of differences of A's. So use that as your starting point to see how the right side can be transformed into the left side using all these equations that you see here. This equation, use this to eliminate the D's. And then once you've done that, this equation, you can use this to eliminate the B's. Yeah, so it's a bit of an algebraic nightmare, but very different from what your own students in 101 think is an algebraic nightmare. And see if you can recover what do you get from multiplying this matrix by this vector. So in fact, what I would recommend is, the B is already written out for you. Go ahead and write out A times C. Like actually carry out this matrix vector multiplication so you can see what you're supposed to get when you rewrite this B vector using those right-hand sides. or sorry, using those equations from the previous pages. All right. Okay. Now, okay, there's a few things I want to point out here, and I admit I'm going to be lazy about it, but it's almost 5 o'clock, so there. All right. Okay, I just want to point out here. Here we have a simple example involving splines. So this deals with natural boundary conditions. So here's some given data. So 5 points altogether, and it steps through a process of solving that system of linear equations from that problem that you've been assigned, and actually getting the coefficients. So this system of equations only gives you the C's. Then you can get the A's, B's, and D's from there. And here's what the spline looks like as 4 different pieces. Because we have 5 points, that's going to be 4 pieces. So you can see how that's obtained. There are actually 2 mistakes in here that I found while preparing the next edition. The known mistakes in the book are posted on my webpage. But if you want, you're welcome to play Where's Waldo and see if you can find them yourself. And here's what the actual spline looks like for this example, that we have a nice smooth function. So this function has 2 continuous derivatives. The third derivative is not continuous. And the third derivative of a cubic will be a constant, and the constants will be different on these 4 pieces. But when a function has 2 continuous derivatives, at least to the human eye, it looks nice and smooth. These problems I would have assigned, except there were mistakes in them. You're welcome. Okay. So the other things I want to mention. Okay. Some properties of cubic splines. Now, a cubic spline satisfies this condition, that its second derivative is smaller in magnitude than any other function that has 2 derivatives, and also fits the same data. Now, you may remember on Monday I showed a similar condition for a piecewise linear spline, except it was a first derivative. So the piecewise linear spline is the flattest function that fits the data. The cubic spline has the smallest average curvature, which would come from the second derivative. And it would be proven in a similar way as for the linear case, but it's a lot more complicated, so I wouldn't dream of assigning it. But that's one interesting property about the cubic splines that minimizes this. And this is for natural boundary conditions. Another thing we're pointing out is this result. So we have the cubic spline with clamped boundary conditions satisfies this bound on the error. So it's less than this constant, where m is the maximum of the 4th derivative in absolute value. And then here we have a spacing raised to the 4th power. Now, last time I showed a similar result for the, I stated a similar result. You actually prove it in the homework for the linear case where it was h squared. For a cubic case, it's h to the 4th. So if you use more and more points, you have smaller spacing between them. The error goes to 0 very rapidly. So that's a nice feature to have of cubic splines. Okay. So these are just certain important properties of cubic splines for different boundary conditions that I wanted to make you aware of. Okay. One subsection I'm not covering is Hermite cubic splines. Now, for that case, what you do is if a derivative values are known, then the Hermite cubic spline fits those derivative values, and forms a nice smooth curve that way. All right, but I wanted to just focus on the most basic cubic splines and how they can be computed. And even though this is not really a numerical linear algebra class, it's worth pointing out that you look at the system of equations that describes the cubic spline for natural or clamped boundary conditions. Okay, here it is. Notice this matrix has at most 3 non-zero entries in each row. So it's called a tridiagonal matrix. So this is a system of equations that is very computationally cheap to solve. So if you have n points, it has so order n floating point operations to solve. So splines, cubic splines can be computed very efficiently. So that's another nice property that they have. Because even though all the pieces depend on each other, they're all coupled together because they have these continuity conditions to satisfy, it's still, at least it's computationally inexpensive to compute. Right, so that's one nice thing that they have going for them. Okay. So now that I've reached the end of new material, does anyone have any last questions about either what I presented or any other homework questions? I need to come up with a rule of thumb for how much awkward silence I let pass in these situations, but or it might be different from one level of students versus another. But it seems like the later you get into the semester, at some point you just like give up and keep going. Okay, but USM students, graduate or undergraduate, are historically a quiet bunch. Okay, so all right, so you have some, shall we say, interesting homework problems ahead. But yeah, I'm interested to see what happens with one from the previous section, dealing with the first one from 7.5 that was asked about. Hopefully when you work that out for this case of small n, that it will click for you. And if not, definitely let me know. So I will, so if there are no further questions, then I could just stop recording here. And if anyone still has questions, of course, I've advised you with one of you coming up after this. Make sure everyone gets advised soon. So set the stage for next semester. Woo! Okay, so all right, I will stop recording at this point.